Hello all, I am Molly Haugen and I am a postdoc here at the University of Cambridge. And today I'm going to be discussing a project I've been working on looking at the future of low carbon energy systems, specifically in the freight sector, and identifying different opportunities and challenges that may lie ahead. This project is in conjunction with the Department for Transport as well as the National Center for Energy Systems Integration. The main objectives of this study was primarily to give a holistic look at the energy system, both the challenges and opportunities within it. This whole system ideology will look at and has looked at how to decrease costs, accelerate the decarbonization rate, and increase energy security within the UK. To do this, I'll primarily have been working on identifying and assessing the evidence gaps that lie in the future energy systems, as well as addressing the severity of those evidence gaps. A few boundaries for this analysis. Looking at different timelines for the future, both 2030 and 2050, looking at the different technologies that are available, giving a national viewpoint to this analysis, so not looking specifically at one location geographically, but rather the whole nation as a combined energy system. My first priority was looking at energy transport, or the energy system from on-road transport, so specifically looking at heavy good vehicles, as passenger vehicles are primarily going the electric route, so that leaves opportunities for both vans and heavy good vehicles to be assessed. Also operating under the assumption that both heavy good vehicles and passenger vehicles will be phasing out fossil fuels. Of course, there's going to be overlap with these on-road vehicles for both rail, maritime, and aviation. But for this specific component of it, just looking at the heavy good vehicle sector. What I've learned throughout this process is that the energy system is really a black box for all of the components that aren't within the silo in which people are operating. So whether people are in the energy generation, if they're distributing the energy, if they're supplying the energy to the user, or if they're actually at the consumer level, the use level, there are different opportunities and challenges that lie within these different silos. And so what I wanted to do is really shine a light on each of those individual, what I'm calling here linchpins, and assessing them individually, but then bringing them all together to give a holistic look at the energy system as a whole, to really making this black box more transparent to different people in different sectors within the energy system. So for example, the energy generation side of things, looking at SMR and electrolysis, how those technologies are developing and what their barriers are, their key barriers are going to be going forward. At how that energy is going to be then distributed from its energy generation point to the refueling and recharging stations. So that is either going to be distributing the hydrogen or distributing electricity, and how that changes then depending on the level of decentralization as well as the consumer demand. And then looking at the refueling and recharging station requirements and what the key barriers are going to be in those different systems. The energy use. This is predominantly going to be dictated by vehicle specifications as well as how the vehicles are used, which will then in turn dictate how much renewable energy needs to be generated, all the way back up the energy production scale. What also is incorporated in the entire energy system is looking at government subsidy timelines, so how long the government needs to be financially involved in the different energy systems in order to make them a viable component to reduce greenhouse gases and to move these low carbon futures forward. Additionally, looking at the actual CO2 reduction capabilities all the way throughout the energy system chain. So yes, you can look at this in individual silos, so looking at the vehicle use if they're replaced with low carbon options, that's obviously going to reduce the tailpipe emissions, but if that low carbon fuel, such as hydrogen, comes from a very carbon intensive source such as steam methane reformation, We're actually just moving that emission to a different location. We're moving it to a different silo. And so by looking at this energy system holistically, we're still able to then address where these carbon-intensive areas are going to keep popping up. How this analysis is going to work is that we'll look all the way back from energy generation to energy use, looking at the key linchpins within this energy system. For example, looking at a hydrogen energy system, where electrolysis is the technology that is being used to produce the hydrogen, all the way to a fuel cell vehicle that is then using the hydrogen. These will be the identified areas that need to be addressed. So then each of these linchpins will be analyzed based off of the barriers that can be attributed to the different linchpins. For example, looking at electrolysis individually, there could be technology readiness issues, scalability issues, or geographical location issues. This will then be assessed based off of literature, both reports, peer-reviewed journal articles, etc. And then given a low, moderate, or high risk level depending on the quantifications here. I will say that depending on the linchpin, these might be changed slightly just so they're more relevant. And there might be areas where some of them just don't apply. But also I will point out, and importantly, that there is this unknown category as well. And this could be either due to a lot of discrepancies within the literature, or that there just isn't literature to support any claims. Both of these are very important going forward with an energy system that may have a lot of unknowns. It seems a very risky move forward if that is the case. So all of these barriers will then be used to address the linchpins within the energy system. So I will say this is very preliminary work. I'm still working on inputting all of the literature data to dictate what these risk levels actually are. But this is an example of how this will look for an energy system using electrolysis all the way down to a fuel cell vehicle. Again, there's the risk level key. And so for an electrolysis energy system going to fuel cell vehicle, these are the components that are a low risk or are well known versus high risk or unknown areas. Importantly, for this pathway in particular, I'm including both fuel cells and batteries. And the scale-up of these is relatively unknown, predominantly because there is very little evidence of what size fuel cells will be required on different vehicles that are using hydrogen. Importantly, Nikola 1, which is the forerunner for hydrogen fuel cell vehicles, for heavy good hydrogen fuel cell vehicles, they actually report that they will need a 250 kilowatt-hour battery on board. And this is not an insignificant size, so both of these being scaled up, both fuel cells and batteries, will be an important component of this energy system as a whole. Also noted on this slide is that the cost of both consumer, or I guess all of the above, consumer, industrial, and national costs is highly unknown or highly disputed. And this is an interesting part of it because cost tends to be a very important factor in moving forward. So that will conclude the semi-quantitative analysis of the energy system as a whole to give a really good look at not only single silos within the energy system, but to be a lot more transparent with what all will be included going forward. An additional part of this work, if I'm able to get to it, which I'm very interested in, is how this system will then scale up. One big component of that is the level of decentralization, the consumer, industrial, national interaction with the energy system. How is this going to change in the future, and what does that then mean for not only the costs of the system, but as well as how well these systems can be integrated with one another and relied on one another. And additionally, what the mode shift is going to be from road onto rail or into maritime, etc. Both of those are relatively unknown, the level of decentralization as well as the modal shift. But I'm very keen to understand that and how that's going to then play out into a future energy system. The conclusion of this project will, of course, be to identify and address the evidence gaps and to give a semi-quantitative analysis of the different linchpins within the different energy systems, looking holistically from energy generation all the way to energy use, and then how to determine what that means for scaling these different technologies up as well. One project deliverable that I'm particularly excited about is working with the Department for Transport in London, where we will hopefully have an interactive site that will allow for all of the work that has been done to be inputted onto, so people can have a centralized location of where to access all this information. Right now I think there's a lot of it out there, and so trying to centralize that into one location. And how that might look could be something similar to a project that they worked on for decarbonizing homes. So having this map that shows how the different components within an energy system will look, and this will be specific for freight. I'm thinking this will include maritime and aviation as well as rail, but my part of it will be the on-road section. And then behind this, having all of the reports, the data, the unknowns, the partially known, the disputed, and having it all in one location that people can then access and add to, hopefully. That's the ultimate goal, is providing a space where all this information can then go and people can actually use it in a condensed area. To give a couple examples of things that I have done as far as accumulating different reports into a consolidated visual would be this image that looks at the cost of an electric road system within the UK from a few different sources. And what both of, or I guess all of, well, both of the main reports show, and I have Siemens in here just to show that it's on the same ballpark as the others, is showing that as an electric road system is more used, the cost actually decreases. Of course, as you increase the maximum number of vehicles that can be operating on an electric road system, the capital cost will increase, but because more vehicles are able to use that, then that actually gets distributed into the amount of energy that's then being supplied to the vehicles. I've also briefly looked at green hydrogen production. So on the left-hand side, we have a graph that looks at the size of the electrolyzer and how that influences the hydrogen production costs. So as we increase the electrolyzer size, we see a decrease in hydrogen production costs. This is the production cost. This is not the consumer cost. So this is what it will be at the initial stage of that. On the left-hand side, we have a bit more complex of a graph from the Hydrogen Council that was based off of some McKinsey work that looks at the load factor of an electrolyzer, which is along the x-axis, the initial cost of the electrolyzer, which is the shading of the different colors, and then the two different colors, one that's highlighted and one that's not, is the cost of the electricity that's coming into the electrolyzer. So we range from 0 pounds per megawatt hour up to about 40 pounds per megawatt hour. What this then means, and what it is showing, is that as we increase the load factor of the electrolyzer, as we decrease the cost of the electricity, and as we lower the cost of the electrolyzer, we will then see a decrease in hydrogen production costs. What this also is showing is that if electrolyzers are being used to store excess renewable energy, That variable load factor could then drastically influence the hydrogen production costs associated with that. So using the semi-quantitative analysis in conjunction with some quantitative information, I think we'll be able to get a really good holistic view of the energy system within the UK and how to move forward within the freight sector of that. And with that, I will conclude my talk and take any questions. Thank you.